Hi, everybody. Thank you for the intro. So I'm David. This is Andrea. So this all started as kind of a quick hack about 2 years ago in 2017. We were looking for ways to improve firmware tooling for what was at the time a new system that was rolling out. And this is the OCP Yosemite version 1 with 4 monolake microservers. So when you're working with firmware and tooling, you tend to spend a lot of time rebooting the system. And you've probably seen something similar to this. So, yeah, all those wonderful, 1-byte postcodes. You have about 256 possible postcodes to tell you about anything that could have gone wrong in the process. But doing this a few dozen times a day got really, really exhausting. So we decided, hey, what if we can improve the way our systems boot? So really what we want to do is just get into Linux as quickly as possible. So the one on the right, firmware's done, we're in Linux. So we went from what you see on the left to booting Linux within a matter of seconds. And this got us thinking of how we might put that on our future platforms, and thus our journey began. So a little bit of background about system firmware. So what exactly do I mean by system firmware? It's sometimes referred to as BIOS, though that term is outdated. It initializes the CPU cores and some peripherals connected to it, as well as certain other crucial devices such as your DRAM. System firmware serves 2 fundamental purposes: initialize your hardware and load a target operating system kernel, usually from local storage or from over the network. So for the purposes of this talk, we'll focus on 2 key pieces of system firmware that we've been experimenting with on our x86 devices, namely coreboot and LinuxBoot. Coreboot is an open source firmware code base that does the basic hardware initialization, brings up the CPU, initializes the DRAM, and so on. It's not a single thing. It's not a single program. It can actually be thought of, well, it actually is multiple programs that are run at different phases in the process, the hardware initialization process, depending on what kind of memory is available. And this is necessary because DRAM is not available when the system is first powered on. Linux expects DRAM to be there. You have to load it into memory and then you have to execute it. So when the system powers on, the CPU just starts executing instructions from the beginning of some fixed location known as the reset vector. The reset vector is part of what's called the boot block. And the boot block is the first program that gets run. And the boot block is it's usually very small, typically maybe a few hundred assembly instructions, and its purpose is to find some kind of memory available that can be used in the next phase. And on x86, we use the CPU's caches as a temporary RAM. So once you have the caches up and running, you can start with the second program, which in coreboot parlance is ROM stage. And coreboot's ROM stage will actually use the CPU's cache to set up a stack so you can start running some normal C code. You're not stuck in assembly land anymore. But things are still pretty quirky at this stage. You don't have nice things like, you still don't have DRAM and you don't have real memory, so you don't have a heap. You can't malloc anything. Your buffers must be statically allocated, and you can fill cache lines, but you can't evict them, so that makes things pretty quirky. So the goal of this stage is just to get DRAM up and running. Once you do that, on to the next phase. So the third program, known as RAM stage, is actually run in, it's loaded into DRAM and executed. So now you have a full C program that's in a much more familiar environment. And this is where a lot of the remaining initialization gets done. So the last thing coreboot does is load a payload into memory and then execute it. And a payload's job is to load the operating system target. A payload can be any ELF binary. It could even be something familiar like grub or Tiano core if you're into UEFI, or even an OS kernel such as Linux. And in fact, in our case, we use LinuxBoot as our payload. LinuxBoot, as the name suggests, is a Linux kernel with an init ramfs that has tools such as kexec, which are used to boot Linux. So this is stored in the boot ROM alongside coreboot. So we actually have a Linux kernel as part of our firmware image. This isn't something that core boot has to read your disks or anything like that. So the LinuxBoot kernel is what we use to initialize storage and networking devices using native Linux drivers. And this means that core boot can be kept very small and simple. Programs running in the init-ramfs environment will then use normal Linux interfaces to hardware. Find the target OS kernel, load it, and then kexec it. Now, this probably sounds like overkill. Like, why do you need a whole OS just to load your OS? But let's think about it for a moment. So let's take a quick look at what's involved in local booting. So you want to boot something from a hard disk or some local storage device. 30 years ago, things were a lot simpler because you had many fewer devices, and you had some de facto standards that kind of stuck around for a few years. And these days, of course, you have a lot more kinds of devices, a lot more controllers, more protocols, and tons of devices from various vendors with different quirks and so on. So just getting the support for the devices has become a lot more complex. Devices these days are a lot faster. 30 or 20 years ago, you had low-speed links. You pretty much power on the system, they'd be ready to go. These days, you turn on a device, probe its capabilities, and ramp up speed of the device and its bus. And this is especially true with high-speed flash memory controllers. For example, NVMe over PCI Express. You probably also have multiple power rails in the system, just basic power saving. You want to turn things off when they're not in use. And for the same reason, you probably have to set up a clock controller because it's no longer assumed that everything's going to be running at full speed all the time, because you probably want to conserve some power when things aren't in use. So simply turning the devices on can require a decent amount of platform-specific work and link training and such. And finally, once you have the device on and you can communicate with it, you have to do the actual work of loading your operating system target and executing it. 20, heck, even 10 years ago, the standard way of doing this was with the master boot record. Basically, what you would do is you would go through your storage devices, and the first thing that was marked on a bootable partition on cylinder head sector 001, you would just load it and execute it blindly. So pretty simple. But nowadays you might have many storage volumes, many partitions, and many possible bootable targets that you want to select from. You may also need to decrypt the file system and actually perform verification of the thing that you're going to execute. So now it's not just find the first thing you can and blindly jump into it. You might actually want to look before you leap. You might have cryptography involved, key signing infrastructure, and so on. So switching gears a little bit, let's take a look at networking. Networks obviously used to be a lot simpler too. And network booting once meant you load a kernel from a server across the room, probably on the same trusted LAN. These days, we like to be able to boot an OS image from a machine in another data center across the world, or perhaps out in the field over a potentially hostile network. And this would be things like your POPs or edge nodes. Like storage, there are many more devices, interfaces, and protocols with varying levels of complexity, robustness, and security. Current network booting technology was mostly designed in the 80s and 90s, like Pixie Boot, which was designed around TFTP. Yay, TFTP. And there are some hacks to modernize Pixie Boot, but we feel it's time that we focus on using protocols that were designed with security and scalability in mind. So think HTTPS and BitTorrent, for example. And just bring network booting into the 21st century. So those are some of the conceptual ways in which booting has gotten more complicated. If you're more into numbers, you can just look at the growth of the related subsystems in Linux over the past 5 years. So here I have some numbers. The blue rows are the source lines of code in a few of these subsystems, like the first one is net/core and net/IPv4 and IPv6. And we see it's grown by about 33% in 5 years, with about 7,500 commits, just in that little subsystem. And this isn't to say that Linux is big and bloated or anything. I mean, it's pretty sensibly developed. It's just the state of the industry. That's just the rate of change. And we see similar trends in other subsystems. For some reason, driver's block actually got a little bit smaller. I don't know if they removed a bunch of dead code or factored some things out or whatever. So long story short is that booting has gotten pretty complex over the years. System firmware has become an OS with drivers, a network stack, crypto libraries, apps, a shell, and more. If we have any gamers in the room, you've probably gotten one of those cool motherboards where you go into the BIOS setup and it has like animated spinning fans. It might have a three-dimensional model of your motherboard that you can rotate and stuff. You know, it's kind of cool, but when you think about it, there's a lot of stuff that goes into that. You know, graphics libraries, maybe even 3D acceleration. So your firmware is an operating system now. And our philosophy is that if we're going to have an operating system in the firmware, we want Linux. The traditional firmware model is totally opaque to the user outside of a few configurations, you know, config variables exposed in the setup screen, or maybe in some config variables stored in the ROM somewhere that you access through the vendor's tool. That's why I chose to represent it with that, you know, lovely black box there on the left. Linux, however, is familiar to us. We have teams of engineers developing and supporting Linux at all levels, kernel, tools, services, etc. We can do anything with it. The traditional firmware ecosystem is also highly proprietary. Users are generally not meant to see any of the source code. But we want the debuggability, auditability, and traceability that comes with using open source software. Keep in mind that this code runs at the highest privilege level and has total access to your memory, storage, and networking resources. So it's important to know what's going on here. Traditional proprietary firmware often comes with its own proprietary tools. From an operations and sustaining standpoint, when we want to go from vendor-specific and sometimes product-specific tools to open and adaptable tools. Traditional firmware is not meant to be portable. Usually you pay a lot of money up front for the vendor to port the code, and then you continue paying royalties for every unit produced. We want to standardize on open firmware that can be ported across a wide range of systems, including servers, networking gear, and embedded platforms. So I had mentioned that firmware has two fundamental purposes: initialize the hardware and load the operating system. But besides those, firmware usually also provides some runtime services. Just because you've booted your operating system doesn't mean that the firmware is completely out of the picture. And like other firmware code, these services run at the highest privilege level and have access to all your system resources. They're not limited by your containers, your VMs, because they run in a whole entirely different privilege context. So on x86, an example is system management mode, but don't think you'll get away from it just by switching to ARM, because they have ARM-trusted firmware. And even on RISC-V, they have what they call M mode. A common example of hardware error handling services which deal with A common example is hardware error handling services, which deal with the errors that occur in DRAM, caches, PCI Express controllers, and the CPU itself. So let's run through an example. So let's say your Linux server is humming along and serving traffic on a bright sunny day. The code that your clients are running are properly sandboxed in a VM, and you're reasonably certain that nothing can break out. Suddenly, one of your DIMMs gets hit by a bunch of cosmic radiation and a bit flips. What happens? Your DRAM controller will hopefully detect that something is wrong and interrupt the CPU. And the CPU will go from running code within, say, Linux, to running code in a black box error handler. The error handler will look at the memory controller registers, try to figure out what happened, maybe log something in ACPI, or communicate with the BMC to log something in what they call the system event log, and then it'll decide what course of action to take. So if the error was correctable, it'll hand control back to the operating system, or if it was uncorrectable, it'll just give up and say memory's corrupt and then reboot your system. This is what's known as firmware first in the industry. Of course, this happens in black box proprietary code, running entirely outside the purview of your security model. So we have drivers, networking, crypto, and more in firmware. We have runtime services, and man, what else could they throw in there? How about a web server? So some enterprise servers have been running RESTful services for firmware configuration for many years. And actually about, about a week and a half ago, the UEFI forum published a new spec that includes RESTful services in it. So, so you're likely to see a lot more of this. And lastly, I'll mention that some firmware-based services might even run on a whole other microcontroller in the system, such as the Intel Management Engine, AMD PSP, and various management controllers that exist on ARM64 and other SoCs. And in many cases, these are wired up directly to your memory and other like peripheral buses. So yeah, things have gotten a lot more complicated. System firmware is now an OS that runs in a highly privileged context, and there are runtime firmware components that are usually a black box. So we want to replace as many of these black boxes as we can with small open source firmware bundled with Linux and user space tools. So our approach is to bundle core boot, Linux, and an inner MFS all in the boot ROM. We want firmware to do as little as possible and let Linux boot Linux. This means we can use the same production quality drivers, apps, and networking facilities that we're used to supporting in the runtime environment. So just to restate that, we want to use code that we use in our runtime environment to boot into our runtime environment. This also enables us to modify and add features and tools, debug, build, and deploy firmware images on our own schedule. We also have a flexible security architecture, which comes in handy when you have various deployment scenarios. For example, are you deploying your server in a highly controlled data center environment with armed guards around it? Or is it going out in the field in a colo or maybe to an end user? You may want the machine to be easily serviceable for the technicians working in your data center, or you may want to lock it down so tight that you can't really do anything with it. So we support multiple security approaches, such as verified boot with a read-only core root of trust, end-to-end measured boot, and we can support different platform security technologies such as Intel TXT, Intel SGX, ARM trusted firmware, trusted execution environments, or Ts as they're called. And most importantly, everything in our world is transparent and reproducible. We know all the components that are going into our firmware, and we can measure them independently. We can also boot in seconds, like you saw earlier on in the demo, earlier on in the presentation. And that reduces downtime and speeds up provisioning, and it also just generally helps us maintain sanity when we have to develop tools or make firmware changes and reboot the system many times over. So we're bringing modern open source development processes and practices to the firmware. Now before I move on, I'm going to go off on a little tangent. Since the Facebook booth is right across from the Bloomberg booth. Whenever I come to an expo and I see Bloomberg, I'm always reminded of that article about a certain hardware vendor a few months ago that had that little hardware implant in it. Real James Bond stuff there. And you may or may not believe everything in the article, and that's fine. But one thing that we can all agree on is that supply chain attacks are a real thing. And as we've discussed, there's already a ton of black box code running in your servers that has practically unlimited access to your hardware and is unconstrained by your security policies, and you have no practical way of auditing or tracing it. So it seems to me like slipping something in there would be a much easier way to commit industrial espionage on a massive scale than what's described in the Bloomberg article. So bringing firmware development out of the Stone Ages and into a modern open ecosystem is not just something that we're doing to feel good. It's something that helps us in our day-to-day operations as developers and users and enables us to become proactive instead of just reactive when it comes to debugging and securing our fleet. Knowing what's running in our fleet is more than just a practical matter, though. It's a duty that we share with our companions in the cloud services industry. We're entrusted with tons and tons of data from personal users, business clients, et cetera. And whether you're a financial services company, a search engine, or a social media company, all this data, protecting it becomes your responsibility. And we know there aren't a whole lot of firmware engineers looking into this stuff, so that's why it's important to open it up to all you SREs and to turn you all into firmware engineers. So where are we now with this? So the stuff we've done is not entirely new. We're building on projects that have existed for quite some time. CoreBoot, for example, is celebrating its 20th anniversary this year and is a member project within the Software Freedom Conservancy. LinuxBoot is a member project within the Linux Foundation. The idea of using Linux as its own bootloader has been around a long time. However, there didn't seem to be a concerted effort to make this a primary use case until the LinuxBoot project came about. And of course, we're part of the Open Compute project, which is an industry-wide effort started by Facebook, Intel, Rackspace, Goldman Sachs, and Andy Bechtolsheim. Facebook primarily uses open source, Open Compute project hardware within our data centers. The Open System Firmware initiative was kicked off in 2018 and has grown substantially since then. I should also mention that Microsoft is participating and working on more of a pure UEFI implementation for those who prefer that approach. Their approach is different than ours, but we've actually found quite a lot of common grounds in that we see a lot of the benefits of opening up the firmware, whether you want to use LinuxBoot or UEFI or whatever. And I just take it as a sign that the industry is ready for disruption in system firmware. One of the first things people usually ask us in the QA session when we're talking about this is whether or not we're deploying it, and the answer is yes. Facebook has started to deploy it as part of our networking infrastructure, and we're also working on it for upcoming server launches. And that Reinventing Facebook's Data Center Network with F16 mini pack, you can just search for that, and it'll come up with a nice blog post. Google has also been a primary driver of this effort and is working to deploy it. If we have any Googlers in the room, you can search for the NERF team, N-E-R-F, in your internal search. And you can even buy servers with LinuxBoot preloaded on it. There's a company called Sesame Open Hardware who refurbishes used OCP servers. And for them, they need something that they can support for their customers, and so they want something open source. And so especially if you're a small, medium business or a university, I highly recommend checking them out. So looking toward the future, we're putting together a schedule for open system firmware, as we call it, to be required as part of OCP accepted criteria. We've decided that March 2021 is a good target, since that's when the 2021 Open Compute Project Global Summit takes place. And it gives the hardware vendors some time to make the necessary changes in their code bases to help us with this. We're developing this as openly as possible and encourage all interested parties to get involved early. 1.5 years seems like a long time, but really it's only like, what, 1 or 2 server generations away? So this could even be part of your next mass deployment. OCP OSF is a great way to get a seat at the table to discuss this with some of the largest hardware vendors in the industry. We typically have engineers from Intel, ARM, WeWin, Quanta, Lenovo, and more who regularly participate in our conference calls. And we invite you all to join us, and we will have a slide at the end with some contact details. And with that, I'm going to hand off to Andrea, who's going to get hands-on with LinuxBoot.
Thank you, David. I am Andrea. I work in the host provisioning and LinuxBoot team at Facebook. And my team is responsible for the host provisioning infrastructure and more recently also of the development and putting in production of the open source firmware. Right. So a quick recap about the LinuxBoot architecture at Facebook. We are using multiple components just like a Linux distribution. We are basically building this system on top of CoreBoot Linux and a couple additional projects that I'm going to mention in a moment. CoreBoot, as David mentioned already, is used for silicon and DRAM initialization because when we boot, we don't even have DRAM working. The system itself is not able to do anything. So LinuxBoot is Linux would not be ready yet to take over at that point. Once CoreBoot has done the system initialization, the basic DRAM and CPU initialization, we hand off the control from CoreBoot to a Linux kernel. I want to stress out that all of this is running on a flash chip, as you can see depicted in the diagram. it's still on the flash chip of your server's motherboard. It's not the target OS. It's not the CentOS or Debian or whatever you're running in prod. This is on the chip. It's on a tiny 8 megabytes, 16 megabytes, whatever size, on your server motherboard. So we are running this Linux kernel, which gives us all the production device drivers, all the friendly and familiar multi-user, multitasking environment, TCP stack, and everything that we are already used to as Linux engineers. All of this is great, but you need additional things to make it work, to make your system work and to make it work as a bootloader. So we have two additional projects called the uroot and systemboot. Uroot is an embedded environment that makes your system behave like regular Linux OS, where you can have all the tools like LSPS, top. You can use it as a base shell for your system. Imagine like a BusyBox, but written in Go in a memory-safe language that is way easier to iterate on, and with some additional cool features that I'll show later on. Systemboot is, we can consider it like a plugin for uroot. It's an additional set of tools that make this system behave as a bootloader. It provides you with a collection of libraries and commands that make it boot either from the network or from local disks that implement TPM measurements. This is basically the collection of all the tools that you use to boot your machine. Then this system, via KXEC, is able to either boot into your target OS, like in the diagram here. It's showing a CentOS running from local disk, where LinuxBoot will basically mount the hard drive, look for bootable OS, and then it will boot it. Alternatively, you can also boot over the network, and I'm going to show this in the demo soon. A bootloader is useful if you can specify how you want to boot. And for this, we are using boot variables, just like in every boot environment that we are already familiar with. On the left-hand side, you can see an example of a boot variable that we use for booting over the network. You can see it's a JSON format because it's easy to parse and read for humans and machines. We are basically storing on the flash chip of the servers these variables in a JSON format on the chip itself. And these are used to select how do you want to boot every time you turn on your machine. On the left-hand side, the example shows that the type is netboot, which obviously means boot over the network. And the method is going to be the HCPv6. It could also be the HCPv4. It could be Slack if you want to do stateless auto-configuration with no external dependency. And then you have to specify other important parameters like which interface you want to boot from. And you do this via the MAC address. There is another flag that you've probably never seen in a bootloader, which is debug on failure. And I'm not going to tell anything now, but I'll show you how this works during the demo. On the right-hand side, there is another boot entry, which, again, it should be pretty immediate to understand. It says local boot, boot from local devices. In this case, a local SSD or hard drive, whatever is attached locally. And it has two methods. One is path and one is grub. The path method simply says boot from this disk with this UID, take this kernel from this path, ramifest kernel parameters, and boot via KXEC. Alternatively, as a transition method, we also provide a grub mode, which will look for a grub configuration file, and it will try to extract the same information from the grub configuration and KXEC into it. So now we have the building blocks to boot from disk and network, which are the two most common scenarios. And we also have security libraries, TPM libraries for verified and measured boots. We said that we run LinuxBoot in production. So this is SREcon, so you're interested in how does this work in production. The short answer is works pretty well, but how do we make sure that it works well before we hit prod? LinuxBoot, one step back, LinuxBoot basically brought software engineering methodologies into firmware engineering. So basically, this brought the firmware engineering world a few decades ahead. And we can use any software engineering methodology that we are familiar with, like unit testing, integration testing, continuous integration, and so on. And this is exactly what we are doing. We do test, since the whole LinuxBoot project is open source and is entirely available either on GitHub or on the core boot and Linux repositories. We can have the regular unit tests from the respective projects. We can have integration tests. All of this can run on the Travis CI or Circle CI or whatever public CI you want to use. This is great, but this is not good enough for mass production. So at large scale, how do you make sure that your system will not break for something that you didn't foresee? Well, end-to-end testing is definitely an answer. We are working on two ways of doing end-to-end testing. One is continuous, and the other one is on demand. Continuous end-to-end testing is basically a way to refresh continuously the test machines and make them boot and verify that they are behaving the way we expect every time, and that they either boot correctly from the network, from local disk, or they can provision until the end. All the results are collected and reported back. So we know when something breaks, like a dependency breaks, the hardware is getting corrupted, it doesn't pass the stress tests, and so on. But we also have an on-demand end-to-end testing, which means that every time you make a change to your own firmware, because let's remember, now we can be firmware developers, we can introduce features and fix bugs. Anytime we make a change to our firmware, the change will trigger from the, in our internal system, will trigger a build of the whole firmware image. It will refresh it on the test devices, and will run tests and report back whether it was successful or whether it failed, and if it failed, what failed. And we are trying to make this as open source as possible. So we are writing a system testing framework that is called Contest, which stands for continuous testing. And this is going to be open source on GitHub soon. So you will be able to do the same with your own machines and your own integration testing. So testing is not the only thing, but of course, once things may still break in prod, so you want to do some troubleshooting. Again, even if it's firmware, now it's Linux, so you have all the Linux tools and experience that you can apply to firmware troubleshooting. If your machine doesn't boot, you can always stop into it, break into a shell. Again, this is in firmware on the flash chip. You can have a shell, and you can run the regular Linux troubleshooting commands. Like you can see, you can use ls, ps, you can use strace, the TCP dump, ping, or whatever traceroute tool. Anything that can run on Linux can also run on LinuxBoot in firmware. Manual testing is nice, but it doesn't scale very well because you don't want to do this for a large number of machines. Automation is what we like to do. So for this purpose, we created a small framework. Again, it's open source on GitHub, and it's part of the System Boot project. This framework is as simple as a checklist that you can run through every time something breaks. If you know that when the network breaks, there are a certain set of things you want to check, like is the network interface up, did it load the driver, is the network working, etc. You can implement your own checks and determine at the time of the failure why and how this is breaking. It's very important to say that at the time of the failure, gives you more useful information than if you do the troubleshooting later on, because the problem may be transient failure, like something that is breaking in your dependencies. So you will not catch the same issue. Maybe you're not able to reproduce the same issue if this happens later on. So doing the troubleshooting automatically when it fails gives you a lot more useful signal. An example usage of the checker framework is a tool called fixmynetboot. And this is related to what I've shown you a few slides ago. Here, the bug on failure is set to true. This means that every time netboot fails on a machine with the bug on failure set to true, this fixmynetboot program will run, and will run this checklist, and will tell you what broke exactly. In the demo, I'm going to show you an example of pinpointing a network booting issue. Checks are not the only thing. You can also try remediations. For example, you can try to load the kernel driver if it's missing. You can try to, you can say, just retry the HTTP multiple times because I know my network is flaky. We shouldn't, but it could happen. Or any other kind of remediation you may want to implement. And if everything fails, you can also tell the firmware, hey, stop and let me troubleshoot manually. Tell me that something is broken, and I will troubleshoot it manually. So this will drop into a Linux shell, and you can do manual troubleshooting. The checker framework is generic, so this is not limited only to networking. You can also do the same for checking local disks. For example, if you're not able to boot your machine into your target OS from disk, you can check whether your disks are present, they are partitioned correctly, the kernel is available, you can read and write from the disk, anything that you can think of. And now I'm going to show you a live demo, so it could break in so many different ways. This is going to be on a virtual machine for simplicity. And I'm going to show you the boot flow. I'm going to show you the initialization of the hardware, then the core boot handing off control to Linux, the RAMFS, the user space tools, and so on. And I'm also going to show you some automated troubleshooting. Now I need a terminal. So what I'm going to do is I will run QEMU for this demo with a custom-built core boot LinuxBoot image. And this image will be configured to try to boot from the network first and then from disk. Of course, if network booting fails, it will try to do local booting and so on, and it will continue in a forever loop. The VM is going to have, of course, network configuration, and there's also going to be an attached hard drive for local booting to show booting from a local disk. On the other side, I have another virtual machine with a configured DHCP v6 server and HTTP server, and I'm going to show you the booting from DHCP and HTTP. This is not going to be visible from here. It should, yeah, even if the last line is cut, it should be visible enough. Is that OK? Can everybody read? All right, a lot of messages. This is going really fast. And yes, I should probably reduce the window size. OK, much better. So what happened here? In a few seconds, we ended up to this point. It says, hello, I am the network installer. It's not a real installer. It's just a demo, so it's not doing any real installation. What happened here is that the system booted, and it did regular network booting. It followed the regular network booting workflow, trying the DHCP and then getting the network boot program over the network, and then it booted into it. In a production environment, this would be starting your installation of your system. A lot of stuff happened before this point, so let's scroll back a bit. That should be a lot, but it's a lot of good information. Well, I guess I can. All right, so what happened here is that core boot started. It initialized memory. It was pretty verbose in showing what's going on. So if something breaks, you don't have the single 2-digit postcode that we saw in the video that David showed us. You will not see just one number and you have no idea what it means. You actually get real log messages. So if something breaks, it will tell you exactly what. Then scrolling down, you see that there is the regular Linux boot messages. It's initializing the PCI Express. It's initializing network stack, drivers, hard drives, and everything else. Then it will get into uroot, the RAMFS that I mentioned earlier. This RAMFS provides us with a Linux environment, but it's not stopping there. It goes into system boot, the additional collection of bootloaders that I mentioned. And here it says, starting the boot sequence, press Control-C within 5 seconds to drop into a shell. It's not what we did. We just let it continue and boot. So let's see what happened here. The bootloader found the boot entries here. The first one says netboot. I want to boot over the HTTP6 and retry at most once. And also debug on failure is set to true. So what it does here is try to boot. This is very verbose. It's a debug build, so I can show you as much as possible of what happens. What happens here is that it goes through the regular DHCP-v6 transaction with solicit, advertise, request, and reply messages. And with all this information provided by the DHCP server, we have a network configuration, so we can configure the IP address of this machine. We also get a boot file. As you can see, this is an HTTP URL. It's not TFTP like you would see on other types of firmware. So what happens here is that the bootloader will just fetch the file over HTTP. It could be HTTPS. It could even be BitTorrent. We are actually using a BitTorrent for booting our infrastructure for several reasons. It's faster, it's distributed, and so on. You can also do measurements if you need security. And then the bootloader, this is the last line of the bootloader, which says, I am doing kexec. I am booting this network boot program. From this point on, this is the bootloader, sorry, the program that we downloaded from the network. It boots, again, it's a Linux kernel, so Linux kernel messages. And it goes again into the network installer. I can show you now an example of what happens when this doesn't work well. So in this case, everything worked pretty smoothly. It booted correctly. Nothing broke. But we are interested in when things go wrong. So in the other virtual machine, on the server virtual machine, now I'm stopping the HTTP server. What this means is that the DHCP transaction will proceed. But when the firmware tries to download the network boot program over HTTP, this will fail because the server is not up. Going back to the client, I'm restarting the virtual machine. Waiting for 5 seconds, and then booting over the network. You will see that it will fail. Red messages. All right, let's go up. Back to what happened. So this is the regular boot flow that we saw in the previous example. This is failing. And it's telling me running fix my netboot on the ETH0 interface. This is triggered by the debug on failure flag that I've shown in a few slides ago. And what it does is run through a checklist, which is first check, does the network interface exist? Does it have the right link speed? Does it have auto negotiation settings correctly? Does it have addresses and so on? The last check is where it fails. It tries to do the DHCP. The DHCP actually works, but the red message says clearly, I hope it doesn't. It's a bit cut out of the. Anyway, this would be a connection refused message. You cannot see it because it's cut, but it says connection refused on port 80. And this is an immediate and clear indicator that the boot flow is failing on HTTP. And we know that this is true because we stopped the HTTP server on the other side. The next line says, no remediation found for ETH0, stop on error requested. So what happens here is that we didn't implement any remediation, but you can implement something like try a different boot method, try to boot from disk instead, report the error through some local logging or whatever you can think of. And this should simplify a lot of your operations, so you know what's happening when it breaks, at the time it breaks, and you know exactly all the checks that have been done and where the failure has been determined. Now, enough with net booting. Let's see local booting. I'm going to rerun this virtual machine, and this is going to boot first time again from network. It's going to fail, and then it's going to boot again from disk because it's the second boot entry. again, failing, checking what's wrong, and then booting from disk. All right, hello, I am the target OS. In a real environment, you will probably boot into CentOS or Debian or whatever your production OS is. Let's scroll back a bit and see what happened here. So the second boot entry, the one that boots from local disk, says, try to look for grub configuration and boot a kernel from that configuration, which is what it does. After network booting fails, it will look for all the disks. It will scan all the disks that are attached to your local machine. And this is very verbose. It's checking a lot of things. But it will try to mount all the partitions with all the file systems that it's able to pick. And eventually, it will find one boot configuration which points to a specific kernel and a specific RAMFS and specific kernel parameters. And this is going to do, again, a kexec. So this, again, is the last line of the bootloader. And this is the first line of the target OS, which would be, again, Debian, CentOS, or whatever. And here we are. So from a bootloader perspective, that would be pretty much everything. But I also want to show you why uroot, the RAMFS, is pretty cool. So I'm going to stop into the shell now instead of letting it continue. When you boot your machine, if you press Control-C when it's booting, you drop into a shell. And you're basically into a regular Linux environment. You can do ls, you can do ps to C processes, you can even do strace. For example, this is running in firmware. It's not in your target OS. You can even do a strace ls and see what the system calls are for your programs. This simplifies debugging a lot. And this is pretty cool because you can build your own firmware image with your own tools. If you need something that is proprietary, you can embed it in your firmware, or you can use the publicly available tools. And that's not everything. uroot is not just interesting because you can do whatever you want with it and put your own tools. But it's also pretty fast to build. To build a uroot image, you just specify whatever programs you want to build into your firmware image, and then you embed it in a kernel image and pack this into the final bootloader. So in this example here, this is the image that I built for the demo. I'm just telling uroot, please build in busybox mode, which means collapse all the programs into one binary, and the symlink will determine what program is actually called. Then I'm telling use all the core programs, use the bootloaders, use fixmynetboot as well, so all these programs are available in the firmware, but also bring some additional external programs like strace or block ID. You can literally add whatever you want. You can even introduce tools to reflash the firmware from the firmware itself. If you've ever built a firmware in your life, you know that it's a very time-consuming process. So let's do it live. Let's see how much time it takes. Hopefully less than 1 hour.
Yeah, so this is for the inner MFS portion. OK, there we go.
Yep.
12 seconds.
12 seconds.
Not bad. But if you're also building the full firmware image, an iteration takes about a minute or maybe 2 minutes or so. So if you're actually developing a lot of tools or the firmware itself, iterating is actually incredibly fast compared to some of the legacy firmware code bases.
Correct. Yeah. The other components that you would build are the Linux kernel and core boot itself, but these are things that you can literally, as David mentioned, you can build in under a minute. And I guess that would be all. Let me just show the last slide.
Do we have some time for Q&A? And Andrea's just going to get some contact info up there.
Thank you.
First question.
Hello.
Hello.
So I want to try that tonight on my desktop PC at home. So how can I access the flash memory where the BIOS is stored? Can I modify it myself? Or I need some special motherboard that are designed for that?
So do you want to try the QEMU target first, or are you eager to try it on real hardware?
I want to try on my home PC, and I want to replace the original firmware by this.
All right, probably the first thing you should do, so it will require support from the firmware, so like core boot in this case. So Google for core boot supported mainboards, and you can see if your desktop board is supported. Our primary target right now is OCP servers, which they may be similar enough depending on what you're running at home. Yeah, expanding the scope of our hardware support is definitely something we want to do, but it requires a lot of hardware-specific changes. So, but definitely, like the virtual machine image is very easy, and that's usually a good first step. And then you can try to hack on your hardware.
Yeah.
Oh, thank you.
Yeah. Additionally, server platforms are not the only target. Anything where core boot can run is a potential target for LinuxBoot. So, for example, Chromebooks all Chromebooks are supported by core boot because it's the official firmware. So you can replace the payload that Google uses for Chromebooks with a LinuxBoot payload and have your own firmware image and flash it with just a USB-C cable.
Cool. Okay. Thank you.
There are also other laptops like the Librem, or there are a bunch of supported boards on the market that you can buy and experiment with.
Yeah, so if you're in the market for a new laptop and you want to try this out, check out Chromebooks, Purism laptops, and I think System 76 just released one too. Okay, next question.
Hello, thanks for the talk. I'm actually a big fan of open source firmware, but I'm a big anti-fan of Linux kexec.
Fair enough.
So is there any way I don't want to, basically, I don't know if it's fixed now, I haven't checked to be honest. Like previously I wanted to get out, to disable kexec on our production systems, but I found that, like, the natural solution let LinuxBoot use kexec to boot the production kernel, but production kernel can have kexec disabled, but that's not the case, obviously. So you cannot boot kexec disabled kernel with kexec, apparently. Is there any way to not to use kexec?
Yes, but it's not our primary target. One of our partners at Google is working on a way to boot any other type of operating system. So kexec can only work with Linux targets. If you want to boot other types of operating systems like FreeBSD, Windows, anything else, we need to support non-kexec booting. This is under work, but it's not our primary target. So anybody who wants to speed up the development is welcome to
actually, I want to boot Linux, but with kexec disabled.
Yeah, no, what I mean is that this is going to be also useful for booting Linux without kexec. Mm-hmm. So if you get enough, if this get enough traction, this can be reprioritized and be part of the project as soon as possible. But yeah, it's on the list of things that we are working on.
Thank you.
All right, and with that, oh, one more?
One more?
I can't resist asking, how do Intel and other people like that feel about this kind of stuff?
Doesn't mind.
Can you repeat the question? Yeah, well, I can, but there's not much.
No.
Okay, so the question was, how does Intel and other silicon vendors and manufacturers feel about this? And actually, the response that we've gotten has been fairly positive, to be honest. I think they're starting to realize that companies such as ours, that they like to call us hyperscalers because we have our own data centers filled with machines of our own design, just like Google, Amazon, Netflix, etc. That they're starting to acknowledge that customers such as us are becoming much more vertically integrated, whereas the traditional firmware was kind of developed with the idea that you're just going to buy an off-the-shelf product and then run that in production. So they've actually been very, very cooperative, and Intel especially has been helping us out quite a lot with this. So we're and also the server manufacturers. Oh, and also the server manufacturers like the ODMs, Quanta, WeWin, our OCP partners. I think they too have realized that as we get more vertically integrated, we want to have more of a proactive role in the development of our servers, and this is something that they can help us with to better suit our business needs. So it's actually been quite positive. All right, thank you very much. We do have some additional resources. If you'd like to chat with us in real time, I recommend Slack or IRC. And if you'd like to participate, we have more conferences coming up, the Open Compute Summit and the Open Source Firmware Conference coming up in the fall. So thank you very much.